Assalamualaikum and very good morning. Today I will be presenting tutorial 5 question 6. My name is Daniel Ramzi bin Muhammad and my matrix number is S75215. Before we dive deeper into these questions, we need to list all the information given in the questions. For example, in these questions, it states that the number of turns in solenoid A is 400 turns and for solenoid B is 700 turns. In these questions also, there is the current in the solenoid A, which is 3.5 A, magnetic flux through each turns, which is 30 micro Quebec, that equal to 300 times 10 to the power of -6, and the turns magnetic flux through each turns of B, which is 90 times 10 to the power of -6, and the rate of change of currents in A, that is 0.500 ampere per second. For question 6a, it requires us to calculate the mutual inductance of M. Okay, for this particular questions, we need to use formula mutual inductance, that is M equal to NB times with the phi VA over IA. So from the previous slide, I have listed the information given. So from the information, we need to substitute the value based on the formula, and we can calculate the value of M, which is M equal to 0.018 or 18 millihertz. Moving on to question 6b. In the 6b, it requires us to calculate the inductance of A. So for calculating the inductance of A, we can define it by the total flux leakage in the coil divided by the current flowing through it. So for for the value of the coil, the total flux leakage in the coil, we can get it by times the phi with the number of turns in the coil. Then we divide it by the number of current. So from the list of the information I have listed earlier, we can get the value 0.120 over 3.50. Then we can divide it to get the value 334.3 millihertz. That is the value of the inductance of A. For the last questions, that is question C, it requires us to find the EMF induced by B when the current in A change at the rate of 0.500 ampere per second. So the magnitude of the induced EMF in the coil B is equal to the mutual inductance multiplied by the rate of change in the current in coil A. So for these types of equations, we can substitute the value from the information given. Then we can get the value 9.00 times 10 to the power of -3, which is equal to 9 millivolt. Okay, for the application in real life, I chose the eddy current sensor. For its operating principle, when a conductive target approaches this magnetic field, eddy current are induced on the surface of the target. The circulating current generates their own opposing magnetic field. This opposing field causes a change in the coil impedance. The sensor electronics detect this impedance change and convert it into the output signal, which is proportional to either distance, thickness, vibration, and the position of the conductive object. Since the measurement is based on the electromagnetic interaction, no physical contact is required between the sensor and the target. The advantage of using the eddy current sensor is the non-contact operations and the high accuracy and fast response. For the non-contact operation is that the eddy current sensor do not require physical contact with the target, eliminating the mechanical wear and tear. This result in the longer sensor lifespan and make them suitable for high speed and moving industrial application. For the high accuracy and fast response, this sensor provide high and precise resolution measurement with a very fast response time. This make them ideal for industrial application such as vibration monitoring, shaft displacement, and the condition monitoring of rotating machinery. That's all from me for this presentation. Thank you.